Let's first take a quick look at lead acid battery used for automobile. The electrode reaction involved for discharge. Remember, discharge is going from chemical energy to electricity when you use the battery. For the negative electrode, okay, where the electron is coming out, of course, that's where the anodic reaction is happening. The oxidation half cell reaction is happening because we are discharging. The electron is coming out from negative electrode. And the electrode reaction is written like this. Again, we are writing the electrode reaction as a reduction reaction, even though it's the anode oxidation, which means in reality the reaction is going from lead side into lead sulfate. So let's check this half cell reaction. Is it balanced in charge? Zero charge on the left, zero charge on the right. Is it balanced in mass? One lead, one lead. Two hydrogen, two hydrogen. Sulfate group 1, sulfate group 1. So it's balanced in both mass and charge. Okay? And the standard electrode potential for this redox pair, the reducing species is lead, and the oxidized species is lead sulfate because lead sulfate does not dissolve much in the solution. Okay, so we write it as a solid. The standard electrode potential for lead sulfate versus lead is minus 0.359 volt versus SHE. That's the standard electrode potential for this electrode reaction. On the other hand, for the positive electrode, where electron flows in during discharge, that's the cathode. That's where the reduction is happening. And we write the half cell reaction as this one. Let's check the charge balance. 0 on the left, 0 on the right. And then let's check mass balance. One lead on the left, one lead on the right. Uh, 4 charge, 4 hydrogen on the left, 4 hydrogen on the right. 6 oxygen on the left, 6 oxygen on the right. So it's also mass and charge balanced. And it is written as usual as a reduction reaction. The standard electrode potential again versus SHE, standard hydrogen electrode for this lead oxide lead sulfate pair would be positive 1.691 volt, positive 1.691 volt. Okay, and the overall of full cell reaction, remember, to go from half cell reaction to full cell reaction, we would like to eliminate electron. This has 2 electron, but this one has 4 electron. We have to multiply the top by 2 and then do subtraction or addition, depending on how you do it. But the goal is to eliminate electron in this process, and we end up with this lead plus lead oxide to form lead sulfate, and in this process also consume sulfuric acid to form water. That's so-called full cell reaction. And then the standard cell potential standard cell potential would be the cathodic standard electrode potential minus anodic standard electrode potential, and it's the positive one minus the negative one, and it came out to be 2.05 volt. That is our so-called standard cell potential for this electrochemical cell or for this battery. Okay, and for practical considerations, when you start to consider practical, what would happen? Then, because we are going from lead to lead sulfate, from lead oxide into lead sulfate. And we need microstructure optimization, because if we only have dense lead and lead oxide, we would have low current density because of limited surface area. And on the other hand, we should not fully discharge, which means uh, convert completely from lead and lead oxide into lead sulfate, because lead sulfate is insulating. Once it becomes completely insulating, when we want to charge it, going back from electricity to chemical energy, quite often it's getting more and more difficult, and quite often it's not exactly reversible. Okay, we cannot get the same amount of charge, or we cannot get out of the same amount of work, electrical work that is put in.